Greetings, my name is Jay McKinley, and for my CS5593 project, I built a web application for exploring and clustering student data. For this presentation, we will travel through an introduction, we will discuss the project's importance, we will discuss some related work, we will propose work, discuss the application's design, the data set, and then we'll discuss some results and conclusions. Customer segmentation is an essential part of almost every industry. Segmentation is an important tool for understanding the makeup of an industry's customer base. This segmentation can allow for targeted marketing, which can improve the industry's bottom line. Another way to improve this bottom line is to improve and customize the service provided for that customer base. The goal of this project is to use a clustering algorithm to segment the student population and to develop some other statistical tools in order to facilitate customer or student segmentation. The reason this project is important is because more than ever, having an education is essential. And as higher education administrators, it is our duty to get our students to graduation. In a recent study, Navient and Impost Public Affairs found that degree holders are more likely to be employed, to score in the good or excellent range of the Financial Health Index, to be homeowners, or to believe that education is a worthwhile investment. From 2003 to 2008, state and federal governments spent over $9 billion on educating the 30% of students that were not retained. And each year, more state funding is taken away from these universities. Therefore, it's important for us to find ways to improve student outcomes while at the same time keeping costs low. Most of the current research done on higher education students in the data mining field has been focused on retention and course success. And the question is, how can we use data mining to help in higher education? Luan proposed a translation of private sector questions, converting them into higher education equivalencies. So questions such as, who are my most profitable customers, could be converted to which students are taking the most credit hours, i.e. bringing the most revenue. Who are my repeat web visits? Which students are most likely to return for more classes? And so on. One important issue to bring up when it comes to doing research in higher education is that unlike many industries, the data tends to be stored haphazardly. In many cases, a variety of different systems all store data separately and then feed that data into, if we're lucky, one central location. Currently, that is the way OU handles most of their data. There are several systems that are all have their own purpose, and then they all share data into one Oracle database, which can be accessed and used to combine these data sets together. Besides that, you'd have to pull the data individually from each Excel spreadsheet or into Excel spreadsheets and then combine them manually, which is what they did in the past. So our proposed work is to focus on, instead of focusing on a single student, the goal of our project is to try to segment the cohort into groups which can have interventions applied in mass. This saves on the cost of providing each student with an individual resource, and also it makes it more likely that we can identify students who need assistance. We also want to build a tool for reviewing student data and statistical information about the sample. Oftentimes, because of the way the data is set up and structured, and because of FERPA regulations, it is not easy for an administrator to get all the data that they need to conduct an intervention. Oftentimes, they don't even know which students need help. And so the goal of this is to provide an easy platform for them to visually see which students are in trouble. And in particular, we want to use the K-means algorithm to segment the student cohort into groups that can be analyzed to determine if an intervention is appropriate. And this is how we're going to do our student segmentation. So for this project, I originally wanted to do the data. I wanted to use student data as part of the analysis. However, because of FERPA concerns, actual student data is not something we can use and share. So what I did is I took that data, and once I kind of explored it a little bit, I was able to develop a simulated student data set using just some basic normal distributions for each feature and create a data set of the same size as the data that would have been extracted from the Oracle database. And I used that to load it into the system, into the application to test whether it would work or not. However, when it came time for classification, it did not work all that well since it was built around normal distributions. So I then used the IRIS dataset to test the clustering algorithm. So first, let's talk about the K-means algorithm. The K-means algorithm is a version of the EM algorithm. So for each center, we identify a subset of training points, its cluster, that is closer to it than any other. And then we find the means for the feature of data points in each cluster are computed, and this mean vector becomes the new center for that cluster. And here you can see we start with the random points, which is in box A. We pick two random clusters, which are the red X and the blue X. Then we find out which points are closest to each one and assign them that category. Then we find the new means based off of each category and move our centroids to there. And we keep doing that until we reach a center point or a convergence point where we're no longer moving, and those will be our clusters. Here's another graphical representation and a version of the algorithm that we would be using. We initialize our clusters. In our case, we decided to use randomly selecting 2 points from our data set and then assigning that as, or not 2 points, but K points as in our data set, depending on what number of clusters we wanted, and then starting that way, and then we would find the distances, assign based on the lowest distance, assign that to the cluster, and then repeat until we reach convergence. And here you can see in the pictures, you can see a 2-dimensional versus 3-dimensional version of that. Here you can see our algorithm designed in R. We randomly get our centroids. We create a list to keep track of all our centroids. We want to return a lot of data back to the user in case they want to use this for anything. And so here we go through, we get our centroids, we add those to the last centroids so we can compare, see if our last centroids are the same as the new centroids. If they're the same, that means we're going to break our while loop. We get the labels, so we calculate the labels based on the distance they are from each centroid. And then we find new centroids, so we get the new means of each one of the new clusters and assign that to be the new centroids. And we keep rotating through until we converge. And then we just return different values that can be used for whatever the user needs them for. All right, so go through the front end real quick. Here's the main view of the front end. As you come in, you can see that it loads in a data set automatically based off of the student data set. I should take that out, needs to be taken out, but I haven't done it yet. So you can load, but then you can load a data set, and this will show you the data frame and all the different values. So you can roll through and see, you can sort them, you can subset them. Here's the next one. You can see we subset it down to just a few of the features. Currently, you can also set the number of clusters. So here we're setting for 10, and you can see over on the far right side, you can see that it's clustering each observation into a different cluster. Next, we have the descriptive statistics. So this goes through the data frame and separates it by continuous and categorical variables, which you can either send it what you want. I haven't built that in yet, but the function does do that. However, here it just takes them and decides on it based on some criteria, whether they're continuous or categorical, and then gives you the descriptive statistics for each one. And so you can quickly get an idea of the means, the mins, the maxes, in a nice, neat format. All right, next slide looks at some anomaly detection by calculating the outliers. It calculates not only the outlier values, but also their index, so for the ability to easily remove outliers. And here we have a plotting tab. So it has several different types of plots, box plot, scatter plot, and it uses the ggplot function. We can select the x-axis or the y-axis. Unfortunately, you can break it fairly easily by picking a categorical variable when it's looking for a continuous. It'll keep working. It just will tell you that you can't make that plot with that data. And you can also choose the feature color. In this case, we picked clusters. You can see the 10 clusters, and how because the data is random, this is pretty much a hot mess, and so you can't really see any clustering. So here, if we take a look at the application itself, we can go in and we can browse, and we can look for we can load in the IRIS data set. And so here we can see the IRIS data set, the different things. So let's look for 3 clusters. You can look at the descriptive statistics, anomalies. So we can see sepal length versus sepal width, and we can see the clustering. And then we can look at cluster descriptions here, so we can pick maybe we want to look at the second cluster and see how its descriptive statistics are differing from cluster 1 or 3. So, conclusions and results. At first glance, not much was learned from clustering the student data. Even with the actual data, which I did run the application on, and this is a project that we in my department discussed as maybe using to identify students. The clustering there's just so much noise in the data that it does not cluster very well. Now that might just mean we need more clusters, or we need to refine the data more. That's something that will need to be done in future work. Also, I tried to make the application fairly versatile so that you could load other data sets and test it in there. Obviously, the IRIS data set worked. The clustering algorithm didn't work perfectly. It didn't only picked out 2 clusters, but that might just be the simplicity of the k-means algorithm. We might need something a little more complex in future work. That might be something is offering different algorithms so that it can cluster in different ways. Well, that is my presentation. I hope that was informative, and I hope you have a great day.